Thank you for inviting me here. And so the title of the talk has some terms from what Prajakta said towards the end of her talk. That doesn't mean that we are going to answer those questions because the model is different. So, yeah, let me just take the pointer. Okay, so the title of the talk is Stability, Popularity, and we'll try to connect these three things in the course of the talk. And this talk is based on three different papers, so as and when they are referred to, I will talk about them. Okay, so while the problem setup is very similar, that is, we have a bipartite setting, that is a set A and a set B. We'll call them applicants or students or medical interns for the set A, and the set B has jobs, courses, and hospitals. However, in contrast to what Prajakta's setting was, here each participant has a preference ordering. So there only one side had a preference ordering. Here both the sides have a preference ordering. And a typical instance can look like this. This is well known as the stable marriage problem. And so the A's are typically called as men and the B's are called as women. When I write B1, B2, it is a strict ordering between B1 and B2. And this is how the instance looks like. So for this instance, we have the preferences are strict, that is, there are no ties. A vertex cannot say that both B1 and B2 are at the same rank, and they are also complete in this example, that is, the underlying bipartite graph is complete. So the goal again is to assign the vertices in A to the vertices in B optimally. The optimally will be modified as we change the problem. So a possible assignment is A1, B2, A2, B1, and now we'll come to what is optimally. So we'll say that with respect to an assignment in this setting or a matching in this setting, we will say that a pair AB which is belonging to the H set but not to the matching blocks the matching if both the vertices A and B prefer each other to their current partners in M. So in this setting, in this example, we see that A1 prefers B1 over its current partner, and B1 has been assigned to A2 that also prefers A1 over its current partner. So A1, B1 is a blocking pair with respect to this matching. So we'll say that such a matching is undesirable in this setup, or this is an unstable matching. So therefore this matching is not good. In contrast, we want a matching which is stable, in which there is no blocking pair with respect to that matching. So this is such a matching is what we desire. So in this example, a matching M prime which assigns A1 to B1 and A2 to B2 is a matching which is stable. A stable matching does not have blocking pairs, but doesn't mean that it will assign everybody to its top choice. It doesn't do that as seen in the example. Yeah, so there are some well-known facts about this stable matching instance or the stable matchings. So whatever preferences you give for the sets A and B, there always exists a stable matching. It can also be computed efficiently in linear time. And if you have the underlying graph as a strict and complete strict preferences and a complete bipartite graph, then all stable matchings are indeed perfect. That is, they match all A's and all B's. So this is well known. So what we will talk about is three variants of this classical stable matching problem and see how a single idea tries to address all the three variants. Okay, so the first variation that we will do is we will have incomplete list. That is, the underlying bipartite graph is no longer a complete graph, but we still have strict lists for the participants. So this is an example where A2 does not have B2 in its preference list. It has only one person, which is B1. The lists are always assumed to be consistent. That is, when A2 does not have B2 in its preference list, B2 cannot also have A2 in its preferences. So in this variation, does a stable matching always exist? Yes, it does always exist. This is also this also follows from the standard result that we have for complete list. And in fact here the stable matching is A1 B1. Note that the graph admits a larger sized matching, the underlying bipartite graph, which is of size 2. So when we go to this model where we have incomplete lists, we have the same result, that every instance admits a stable matching and it can indeed be computed in linear time. However, the result that we had, that is all stable matchings are perfect, no longer holds true, but an analogous result is there, that is all stable matchings have the same size. In fact, they match the same set of vertices that is known, that from which it follows that they have the same size. But as seen in the example, a stable matching which is A1 B1, which is of size 1, and the largest size matching in this instance has size 2. Therefore, a stable matching can be half the size of the maximum cardinality matching. So one can ask, can you relax this notion of stability and can you get a different notion of optimality such that you get larger size matchings? So this is the first variation, and this is the goal in that variation that we are looking at. So any questions till here? Okay, so we'll go to the, yes, stable matchings will at least be, because they are maximal matchings. Yeah, so they will be at least half the size of the maximum matching. Yeah, so now we'll go to a second variation where we had allowed incomplete lists earlier. We will allow what is called as ties, which happens in practice. That is, now we allow vertices to have both A1 and A2 ranked at the same rank, that is, they are both at their top choice. So we need to slightly redefine the notion of a blocking pair. We'll say that an edge which does not belong to a matching blocks the matching if both A and B strictly prefer each other to their current partner. Because there are ties, we need to introduce this notion of strictly preferring. We'll again ask the same set of questions. Does a stable matching exist? Yes, it does exist. And now there are two different matchings. The earlier matching, which is A1 B1, which is the old matching which we had, which is stable. The other matching, which was the larger size matching, which was blocked by A1 B1, is now no longer blocked by A1 B1, because while A1 does like to move to B1, B1 is indifferent between A1 and A2. Therefore, it is okay for it to be assigned to A2 versus A1. So therefore, B1 doesn't participate in the blocking pair. Therefore, both these matchings now are stable. So now what we know is that every instance does admit a stable matching. It can be computed in linear time. Now, as seen in this example, all stable matchings need not be of the same size. There are matchings of different size. And again, a stable matching can be half the size of another stable matching. So one would like to ask, how can we compute largest size stable matchings in this instance, in this variation? So this is the second variation, and we have this is the question that we would like to pose. So the third variation is what Prajakta was talking towards the end, which is called as lower quotas or demands. That is, we now go back to preference lists being strict. They can be incomplete, that is, the underlying bipartite graph is not complete. However, in the output matching that we have, some vertices must be matched. So these are given to us as a part of the input. So in this example, if I underline this vertex, it means that this vertex is a lower quota vertex. Actually, the motivation is, it is more interesting when you have capacities, and many of these results will hold for capacities. But for the purpose of today's talk, we'll just talk about one-to-one settings. So A2 is a vertex that must be matched in every matching that we output. So then, does a stable and feasible matching exist? Now in this example itself, we can illustrate this. That is, the only stable matching is A1 B1. This is stable, but it does not match A2, therefore it is not feasible. the only feasible matching, or there is one more, but the feasible matching that is there, which is M1, which, so this should have been M2, A2 B1 and A1 B2. This is feasible, but it is not stable because it is blocked by the pair A1 B1. And now it is known that one can answer this question, that does there exist a stable and feasible matching, and this goes back to the comment that I had made, that every stable matching of the instance matches the same set of vertices. So if you wanted to know whether this instance admits a stable and feasible matching, you just forget about these vertices which are lower quota vertices, compute a stable matching and ask, is this feasible for you? If that matching is feasible, then every stable matching is feasible, else no stable matching is feasible. So therefore, in linear time, we can check whether the instance admits a stable and feasible matching. Now, one would like to ask, if there is no stable and feasible matching, what is a notion of optimality, and how should we define that to get optimal matchings that are feasible? So these are the three different variations that we have defined, and we'll be talking mostly about variation 2. And but before we go to variant 2, we'll talk about quickly about the classical model, that is the strict and complete list, just as a quick recap. Yeah, so before this, are there any questions about the three models? Okay. Okay, so going back to the strict and complete list, when we had this, we said that we have the underlying bipartite graph is complete. We have all preferences as strict. We want to compute a stable matching, and this is done by the very well-known Gale and Shapley algorithm, which was given by them in 1962. So this is a proposals algorithm. One side of the bipartition proposes, the other side accepts or rejects based on the proposals that it gets, and the order of proposals doesn't matter. So we just start with A1. A1 proposes to the top choice B1. It accepts it because it has nobody currently. A2 proposes to B1. B1 now looks at its preference list and says that I am currently with a better partner, so it rejects this, and so on. So A2 then goes ahead and proposes to the next vertex in its preference list, and it accepts it. So at this, the algorithm stops and you have everybody matched, or you have that some, in case you have incomplete list, you will have that some vertex which is unmatched has exhausted its preference list. So it is, so the matching that we get is MS because it's a stable matching, and it in fact it is easy to show that it is stable. In fact, the order of proposals doesn't matter, that is, irrespective of what order you make the proposals, you'll always get the same stable matching. The instance may admit multiple stable matchings, and the side which proposes does matter. That is, if you had the B side proposing, you could have obtained a different stable matching. So what we have done is we have these four things, the classical setting, and for that we have seen the simple algorithm by Gale and Shapley, which computes a stable matching for the strict and complete list. So as I said, we will go to variation 2 because that is how this idea was developed in time, and therefore we will present that idea first. So to recall, we have incomplete lists with the vertices, and we allow ties in the preferences. So again, ties can be on both sides, but for this example, for this talk, we'll assume that ties occur only in the preferences of the B side, and the result that we'll be presenting is only for that. So we have seen that such instances may admit multiple stable matchings of different sizes, and in fact in this instance there were two stable matchings, M1 and M2, and one of them was double the size of the first one. So the natural question is to compute the largest size stable matching, and this is NP hard even for restricted settings. So one would like to ask, are there good approximations to this, the size of the stable matching? So sometimes it is also called as a weakly stable matching, because we say that whenever a pair is blocking, it strictly prefers each other to the current partners. So a simple method is just break all ties arbitrarily and run the Gale and Shapley algorithm, the algorithm that we had shown earlier. While we had shown it only for complete lists, the same algorithm can be run for the incomplete list. So we just break ties arbitrarily. If we break ties arbitrarily, we will we'll get a matching which is a stable matching, that can be easily seen, because between the two vertices that have ties you do not change any order. But you can get a matching which is the smallest size, or you don't have any guarantee on the size of the matching. So we'll get a stable matching, but there's no guarantee on the size. In fact, in this example, if you break the tie as A1, A2, then you will get the one size matching. Yeah. So and because it is a stable matching and it is maximal, it is guaranteed to be half the size of the maximum matching. So that that trivial guarantee we'll get, but we do not get any non-trivial guarantee. So while this problem looks like a small problem, there has been a lot of work in this to get good approximations. One, which develops techniques. The second, it also improves the guarantee, and because this is a practically useful problem. So this was known, this 0.5 is trivial. Manlove and Irving gave a 0.6 approximation. This was improved by Kirae to 0.66, which is 2 by 3, 0.6666, which is 2 by 3, and this is what we will be concentrating on. I'll show you this algorithm and how it connects to the other two variants. Subsequently, Iwama and others, they improved the guarantee to 0.68. There's further improvement, and the latest, which is by Lamb and Plaxton, which is in 2019, gives a 0.73 approximation to this problem. On the hardness side, there is a 0.9, about 0.9 hardness of approximation known, and there is still some gap here. So we'll be concentrating on this part, which is 0.66. Some of the techniques, some of the algorithms here are using the idea of Kirae. Some of them are slightly different, which also use LP-based algorithms. So this algorithm is due to Kirae, who gave it in 2011. So the idea is very simple. It says, let's do two executions of the Gale and Shapley in the following manner. In the first time, you break ties arbitrarily and run the Gale and Shapley algorithm like we would have done for the naive setting. Then unmatched A's, there may be some unmatched A's. If all A's get matched and the first A's, there is nothing to do. But if there are unmatched A's, they propose with what is called as increased priority, and the vertex B to which it is proposing uses this increased priority for breaking ties. Recall that we always need to maintain stability. So if there is a strictly preferring vertex, we should use whatever the preference order tells. But whenever there are two vertices which are in tie, then we will use this increased priority for breaking ties. So because we are never violating the strict preferences, therefore stability will not be violated, we'll get stable matchings. We need to argue about the size. So before we go there, we'll just execute the algorithm on this instance. So we have broken ties arbitrarily. In fact, we have done that in a way where we have A1, which is strictly preferred over A2. So the algorithm runs as follows. A1 proposes to B1, and this gets accepted. A2 proposes to B1, this gets rejected by the strict order currently that is there. Now this is where this unmatched A's proposed with higher priority kicks in. That is, we show this higher priority by a star. So A2 star proposes to B1, and at this stage B1 evaluates this proposal with respect to its current partner. If A1 and A2 were strictly ordered in the original preference list, it would have rejected it. But because, recall that they were in ties, it uses this star to give higher priority to a star marked vertex and accept that proposal. What does A1 do? A1 has still not exhausted its preference list, so A1 goes ahead and proposes to the next vertex in its preference list, which is B2, and this vertex now did not have any partner, therefore it accepts this. So at the end of the algorithm, we have A1, B2 and A2 star B1, but this star is only for the purposes of our algorithm, and therefore we forget that star and output the matching, which is A1, B2, A2, B1. So this is how the algorithm runs. Yeah, so as we have said, since we are never violating strict yes.
Imagine that when I'm doing unmatched training, I have two guys who are still in trial. Still they have ties among each other.
So they are unmatched and
they still have ties.
Okay. So right now we are assuming that A's do not have ties.
Okay. So suppose even if it was A's.
Yes.
Right. So when you are saying that, so like when A's propose second time, why it cannot happen that I still can do the tie situation, and hence I do not know how to increase the priority.
Okay, so if you have two A's which are, so there are four conditions that can happen. So there are two vertices without a star which propose, then B knows what to do. Yes. Then two vertices which are with a star, then it doesn't change its partner. If they are at the same this thing, so it changes its partner only when it is absolutely asked to change. Yeah. Okay, so in fact it can be, it can be, to write it you can give a rank of plus epsilon between them and minus epsilon between them and then do that strict ordering. Yeah, so to argue about the size guarantee, what this algorithm does is it shows that there are no short augmenting paths with respect to the optimum matching. That is, in fact, this shows that if you look at the output of this matching, in this case it happens to be the maximum size matching, but since it is hard, you don't expect it to happen on all instances. We'll show that when you look at the symmetric difference of this matching and the optimum matching, there are no short or 3-length augmenting paths. In fact, there cannot be 1-length augmenting paths because it's a maximal matching. There will also not be any 3-length augmenting paths. So this may be well known, but I'll just flash the slides quickly. So this is any bipartite graph. The red edges form a matching. This is not the largest size matching because there is an augmenting path. An augmenting path is an alternating path which has both its endpoints as free, and all augmenting paths have odd number of edges in them. So whenever you do not have 1-length augmenting paths, these matchings are maximal, and if you do not have 1-length as well as 3-length augmenting paths, then one can show that the matching is at least 2/3 or 0.66 sized of the maximum matching. This is what exactly we will use. So we'll come back to the Kirai's algorithm. So we said that break ties arbitrarily, execute the Gale and Shapley algorithm, then unmatched A's propose with increased priority, and B uses this increased priority for breaking ties. So we'll show that there are no 1 or 3-length augmenting paths with respect to the matching that we have when we look at the symmetric difference between that matching and the optimum. So we'll make some observations about the algorithm. So if a woman B is unmatched at the end of the algorithm, then it means that she must have never got a proposal, because if she got a proposal, this is true even in the Gale and Shapley algorithm. So if she got a proposal, she only rejects it for better and better proposals. So if a man at the end of this algorithm A is unmatched, then it must have got increased priority and it must have proposed all the B's in its preference list with the increased priority, and even after that it has remained unmatched. So these are the two simple observations which are useful. Okay, so suppose we ran the algorithm, we had the matching M, and when we looked at the symmetric difference with respect to the optimum, it does indeed have this 3-length augmenting path. So this 3-length augmenting path has A2 B1 edge coming from the matching, which is this M algo. The gray edges are the matching, the optimum edges. So what we will observe is that A2 never proposed to B2 because B2 is unmatched after the algorithm, at the end of the algorithm. This implies that A2 did not get increased priority because A2 has not even proposed to everybody in its preference list. So therefore it implies that A2 did not get increased priority, which also implies that A2 strictly prefers B1 over B2 because it went in its order. Therefore A2 strictly prefers B1 over B2. So okay, so the idea is to show that this cannot happen. That means A2 B1 is indeed a blocking pair with respect to the optimum matching, which is the gray edges. That is why we want to establish that A2 strictly prefers B1 over B2, and similarly we want to show that B1 strictly prefers A1 over A2. Yeah, also I would like to recall that we have established that A2 strictly prefers B1 over B2. A1 is unmatched at the end of the algorithm, so A1 must have got higher priority. So A1 proposed with the star and it still remained unmatched. So A1 must have proposed to B1. At that time, we don't know what it was matched to, but it could have been matched to A2, and if it rejected A1's proposal, then it must be the case that it prefers A2 strictly over A1, otherwise it would not have rejected the proposal, and therefore we have established that B1 also strictly prefers A2 over A1. So therefore we have the desired result that both A2 and B1 strictly prefer each other over their current partners in the optimum matching, which implies that the optimum is not in fact stable. Therefore it cannot happen that it has these 3-length augmenting paths. So this finishes the proof that this output of the matching, when you looked at the symmetric difference with respect to opt, does not have any 1-length as well as 3-length augmenting paths. Therefore it is at least 2/3 the size of the optimum matching. So what we'll just summarize this variation. That is, we have a simple extension of the Gale and Shapley algorithm, which gives us this 0.66. The earlier results use some different ideas and slightly more complicated ideas as well. This algorithm extends a slightly different algorithm also extends for the case of two-sided ties, where there are ties on A side as well, and it also extends to the case where you have capacities on the B side, which is what is called as the hospital residence problem. Yes.
What happens if we take Kirani's algorithm and run several?
Yes. So in fact, several rounds and slightly different ways of proposals is something what gives better guarantees, and also then use of an LP to just instead of giving this just increased priority, give it based on the solution of the LP, gets better approximation guarantees. Yeah, and this increased rounds will come into play in another variation that we'll talk about. Yeah, so what we have done is we have, again getting back to the table, we had this classical setting for which the Gale and Shapley algorithm works. For this variation 2, we have seen a modification of the Gale and Shapley algorithm which gives us an approximation to the largest size stable matching. So now I'll have little bit of time to talk about variation 1 and variation 3 and see how this similar idea is used for addressing the two questions there. So before I talk about it, I'll define this what was alluded to in the last talk about popularity. So this is an alternative to stability, and it was defined in the context of stable matchings by Gardenfors in 1975, and it says that we'll talk about, when we talk about two different matchings, we'll compare them by votes of the participants. So if you had two matchings MS and M and you wanted to compare them, you will use the votes of the participants. So you'll say, you'll draw a table which is all the participants A1, A2, I should have drawn B1, yeah, there is B2 also. So B1, B2, and ask which matching do you like between M and MS. In this case, these are the two matchings. So A1 says I get the first choice here versus A1 is unmatched, therefore it likes MS. A2 says it likes M over MS because it gets matched here versus being unmatched. B1 says that it likes MS, and so B2 is unmatched in both, therefore it doesn't matter, and therefore it is not there. So so a matching, so in this case we see that the matching MS gets 2 votes versus M which gets 1 vote, therefore we say that the matching MS is more popular than M, and a matching that cannot be beaten with respect to these votes is called a popular matching. So does a popular matching exist? In this setting where you have two-sided preferences, it is guaranteed to exist because one can show that a stable matching is popular, therefore a popular matching does exist. However, if we look at these two different matchings, one which is MS and the other which is M prime, which is the two-size matching, now we see that while the other votes remain the same, this B2 is now matched in M versus being unmatched in MS. So B2 also votes for M. So now it is no longer the case that MS beats M, and in fact in this simple example it is easy to verify that there is no other matching that can beat neither MS nor M. In fact, MS can never be beaten because it's a stable matching, and stable matchings can be shown to be popular. In this example, M prime also cannot be beaten, and therefore this is also a popular matching. So while this is not a proof that it is popular, it just says that I'm just hand waving and saying that it is indeed popular. The stable matching is always popular, but now it also shows this example, if you believe me that this matching M prime is popular, then there are larger matchings than the stable matching which are also popular. So one can ask, can you compute the largest size popular matching in an instance where there are preferences on both the sides and the preferences are incomplete but the preferences are still strict? And note that this is not meaningful in the case of complete lists because all stable matchings have the same size and they are perfect, and therefore all stable matchings are indeed the largest size popular matchings. So so in fact this question was considered by Kavitha in 2012. In fact, even prior to this, Kavitha and Huang considered this and gave a different algorithm. But this algorithm that she gave is based on this, or is a variation of this idea where you give increased priority. However, the difference is that remember, there are no ties now. In case of Kiraya's algorithm, we said that whenever there is unmatched vertices, they will be given higher preference and bees will take a decision based on their ties. Here, unmatched vertices will be given higher preference, and this increased priority vertices will always be given higher preference over a normal vertex. Therefore, we will have violations of stability. That is, stability may in fact be violated, but we are okay with that. Remember, the matching M prime that we showed was certainly not a stable matching. It did have blocking pairs, but it was a matching which could not be beaten. So what one can show is that if the same idea of Kiraya is used, that is, if you give a higher priority to unmatched vertices, in particular A1 applies to B1, A2 applies to B1 and gets rejected, but A2 star applies to B1. Even when there is a strict list, B1 will accept A2 star because it is a higher preferred vertex over the normal vertex. It will accept it, and then A1 proposes to B2. While we get the same matching, one can show that that matching is popular in that instance, and in fact it is a largest size popular matching. So I won't be going into the proof of that, but what one can show is that the matching that one produces is at least the size of the stable matching, and it is at least 2/3 the size of a maximum cardinality matching in the instance. This proof is again on similar lines by showing that there are no 3-length augmenting paths, and because every vertex gets at most 2 chances to propose, it is again a linear time algorithm. So in fact, a similar idea of giving increased chances of 3, 4, and if you give at most n chances to the vertices, where n is the number of vertices on the A side, then you can get a matching which is the largest size matching, that is the maximum cardinality matching, and amongst all the maximum cardinality matchings it is popular. That is, it may not be a popular matching, it may still be beaten by a smaller size matching. For example, a stable matching may beat it, but amongst all the maximum cardinality matchings it is a popular matching. So this is a similar idea, that is, run Gale and Shapley, unmatched vertices propose with increased priority, and this can be done multiple times, as many as n times is sufficient to get a maximum cardinality matching. And in fact, in Kiraya's original paper, he says that he thought about this idea to teach maximum cardinality matchings in a different way. So as I have said, stability may be violated, but in this case the guarantees on the input is that the output is a maximum cardinality matching. It is popular amongst maximum cardinality matchings, and its running time is mn because we give n chances to every vertex. So a few minutes on this last variation where we have lower quotas associated. So in this case, recall that we go back to strict and incomplete lists, but there are some vertices which must be matched, and we have seen that there may not be a stable matching which is both feasible. So what we ask is, does there exist a matching which is popular, but it is only popular amongst the set of feasible matchings? That is, if you look at all the feasible matchings in the instance, that is there a matching that cannot be beaten by any other feasible matching? And in fact, in this example, the matching M prime happens to be such a matching. The only other feasible matching is to match A2 to B1, which is a smaller sized matching, and that is clearly not beating this. So the idea of this, so this work was done with Prajakta which appeared in 2017 in FSTTCS, and here what we do is we run the Gale and Shapley algorithm. If that returns a feasible matching, that is both feasible and stable, and we are done because a stable matching is popular. If it is not, then we'll give the vertices which are unmatched, the unmatched vertices, we give them increased priority. This is the same step that was there in Kavitha's algorithm. The next is, if we still do not get a matching which is feasible, then we let deficient vertices, that is vertices which have lower quotas but they have not they have not been matched. Again, propose with even increased priority, and we show that yes, stability will be violated, but there at most n chances are required, and at the end of this we will get a feasible matching which is popular amongst the set of feasible matchings. So yeah, so I am not even attempting to give any hand wavy proof. So the guarantees of our algorithm are that it is guaranteed to be feasible. It is a maximum sized popular matching amongst the feasible matchings, and since we give n chances, it will again run in order mn time. So as I said, there were three things that we were supposed to look at. We looked at variation 2 in some amount of detail. Variation 1 and variation 3, we just scratched the surface. We defined the problems and said that the same technique will work. In each case, it's the idea of giving multiple chances. However, there are several non-trivial details in terms of the proofs, etc. And all these algorithms can be written as a reduction. That is, you can construct a suitable stable matching instance. In fact, in our FSTTCS paper, we just we construct a big instance of size mn and then run the Gale and Shapley algorithm on that, and then show that output of that in fact can be mapped back to a matching here. And much of the thing that I talked about works in case of at least one-sided preferences, one-sided capacities on the B side. Some of it also works for two-sided capacities, that is the many-to-many setting. Yeah, so that's all I had to say. Thank you.